Okay, so this is the fourth chapter. We finished the simpler chapters, so now everything is not complicated but very interesting and details. So you must read carefully in case I missed any of the points. Okay, but the podcast should help you get ready and read the book more easily. Convection, I think you already know what that means. We had looked at, well, maybe not in this course, but you can think of a room with a heater in one corner, and slowly the room warms up. How? The air near the heater gets warm, it rises, hits the roof of the room, ceiling of the room, then goes around and comes down to serve more air to fill in the rising air. So the advection of the heat by the air setting up this circulation is convection in a simple way. So the most important thing, it turns out, that is it's not directly forced. It's kind of set up by instabilities. So the heating sets up the air to get warmer. Warmer air gets lighter, it rises, and then air has to come in and fill that for mass continuity. So we'll see the kind of instabilities that are needed. Some of the important characters in this business: John William Strutt, who became Lord Rayleigh, was the first to study convection and establish the theoretical basis with his amazing papers in the early 1900s. Rayleigh-Benard convection is something you may have heard of. And there is Clausius. We talked about the Clausius-Clapeyron equation, the nonlinear relation between vapor pressure and temperature, exponential BT. Remember, that's the guy, and he was the one who brought thermodynamics to be applied to these problems, having applications everywhere, because his second law of thermodynamics, delta Q equals du plus dw, is basically what tells us that entropy tends to a maximum. Now we try to apply it to the universe, the expansion of the universe, what would happen to the universe in the end, why does milk tend to spontaneously split and go bad, but it cannot go back? Why can egg spontaneously break, but it cannot reattach, and so on and so forth, right? So Howard, the other personality in this business, was actually manufacturing chemist and pharmacist, and he was an amateur meteorologist. There are lots of fantastic amateur, as we say in India, meteorologists in the world, and on Facebook now you have lots of people posting their own analysis using satellite data and model outputs from the operational forecasting centers and so on. And some of them are very good, whereas some of them are not so good. So you have to find out who is good and who is not good, but this knowledge may help you figure out who is just reading Wikipedia and posting something. Okay. So we had done radiative balance, and we had also looked at hydrostatic balance and said radiative convective balance is going to be driven when there are instabilities in the system. The simplest way to imagine it is that you have a surface which is warm at 288 Kelvin average temperature, whereas the atmosphere is emitting to space at 255 Kelvin. Remember, we did the energy balance of the incoming short wave and outgoing long wave, right? So there you have a warmer surface and a cooler upper atmosphere, and the solar heating is obviously mostly getting through the atmosphere to the surface and creating heating from below, right? Warm air is going to rise. This is what is going to drive our atmospheric circulation. So you have a cold top and a warm bottom. So you have these convection cells. It's not that simple, because the temperature decreases with height. Doesn't mean density increases with height, because density also depends on pressure. and pressure decreases with height. So temperature is getting colder, may want to make the air heavier, but the pressure is decreasing, which will make it lighter. So you have a instability that is needed to drive these circulation. So one of the most important concepts we'll learn here is called a parcel of air. What do we mean by that? Basically, we will move parcels of air around, and we'll see how temperature should change and what hydrostatic balance would mean to the pressure of that parcel that's being moved around. Okay, so it will turn out that hydrostatic balance is such a strong constraint that typically the pressure of the parcel and the pressure of the environment, the air around, tends to be equilibrated, whereas the temperature can be different. So the buoyancy comes from this temperature difference but same pressure. Okay, next we're good instabilities. So there is our hydrostatic equation, partial pressure of partial derivative of pressure with respect to height plus g rho is 0, or we wrote it as dp dz equals minus rho g. So how is the motion induced when the net force is 0? What do we mean by that? You remember we had pressure from the bottom, pressure at the top, and we had gravity pulling the air parcel down, but the pressure could balance it to give us hydrostatic balance. So as I said, the motion is not going to be directly forced in that sense by force balance, but it's going to be driven by instabilities which have to be converted from, let's say, potential energy into kinetic energy. That's how the motion tends to be driven. Then we have to explain why there are horizontal homogeneities and how a cold air at the surface at high latitudes that is heavier than the warmer air in the tropics at the surface can maintain their horizontal gradients. This turns out to be a amazing scaling that we will look at. Okay. So convection in a shallow fluid, this is just a schematic. If you create a heating from below, we will see an experiment that's a cute experiment presented in the book, and a cold top, then the warm liquid wants to rise and the cold liquid wants to sink, and if you don't rush the process, then this can set up very nice cells that are easily observable. Of course, this also depends on viscosity, because as you can imagine, maybe in a liquid like water or milk, you can set up such a convection by heating from below. But if you try to do that with, let's say, liquid molasses or honey or oatmeal, it's not going to convect so easily. It's going to start bubbling. Bubbles are going to start popping because viscosity becomes very important as well for convection. Okay, that's kind of the very basics. Now we will get into more and more details about how the instabilities are set up, how potential energy is created, and how that can get converted to kinetic energy and set up the motions.